In this segment, we'll look at repeatable read isolation. And we'll also look at row locking and at the issue of transaction deadlocks. So let's start by repeating the process from the prior segment using repeatable read isolation. At this point, the Baker account is 800, and we'll do the add of 50 and 100 in the two sessions, but we're going to omit session 2's initial mistake and rollback because we're not really dealing with dirty reads anymore. So session 2 will just do a update of row 3 to 900 and then commit it. So with that in mind here, session 1 does a set transaction isolation to repeatable read and starts a transaction and fetches the current state. So there's the 800 there. And then session 2 is going to likewise start a repeatable read transaction and find the 800, select star from account, update it to 900, and commit it there. Now, if we go back up to session 1 under repeatable read, does an extra select, what we see is that the result is still 800, where under read committed isolation it would have been 900, session 2's newly committed value. Repeatable read isolation ensures that any value read during a transaction will be repeatably readable as the same value throughout the transaction. But again, MySQL accomplishes this by giving session 1 a copy of the original row 3 value, and as a result, session 1 still bases its addition on that now outdated value, and it winds up overwriting the value written by session 2, leaving us with the 850. And session 2, rather to his irritation, has tried 3 times to get his $100 added and has not had any success so far. Now, doing a repeatable read via a copy of the original data technically meets the standard, in that session 1 repeatedly sees the same value for row 3 throughout its transaction. But a different DBMS might have blocked one session from reading the possibly changing value, blocked session 1 for instance, until the other had completed its changes. So MySQL says, we'll make your reads repeatable by hiding all changes, even committed ones, until your transaction's done. And a better solution might say, we'll stop you from viewing any data that is potentially about to change until the new version is committed, so you can repeatably see the latest or most recent version. One transaction would have to wait, but neither would have their work based on outdated values. So how do we make this happen under MySQL? You can get MySQL to use a locking approach and fix the problem of updates wiping one another out by adding forUpdate to the end of the select statements. So as here we have select star from account where ID equals 3 for update. Now, the forUpdate causes MySQL to lock the row in question, blocking any other write on the row until the current transaction is committed or is rolled back. Now, this is something to use judiciously, since it will cause other transactions to wait, and that's why we narrowed the select down to just row 3 here. Now, if another transaction also wants to modify the row and executes a similar select for update, session 2 for instance, its select will block until the first transaction is done. You can see that in our session 2 illustration here, where the select only returns after session 1 is done. And when it does, it'll show the correct values. So let's finish up session 1 here, and that will update the balance to 900 based on the 850. And then when we commit it, now session 2's select returns, and it sees the 900, the correct value, and adds $100 based on that correct value, and thus finally we get the session 2's addition done after session 1's, and they're both in effect in the database. Thus, now a quick way, by the way, to get the same effect if your modification is simple enough, is to do the computation entirely in the update command without a preliminary select at all. So you could say instead, for instance, start a transaction in session 1 and in session 2, but do update account set balance equals balance plus 100, right in the immediate set command there without a prior select to add 100 there, and then the add 50 in session 1. And what we will find is that each update command runs as an atomic, uninterrupted action and then locks the row in question so that no other update on it may run until the first update's transaction finishes. In the case of our example here, that was session 2 that had the first one, and so when we commit session 2, then session 1's update runs, commit session 1, and we can find that both of them succeeded. Now, this approach does require that you make a modification simple enough to describe in a single update. Otherwise, you have to fall back to the select and update pattern we had earlier. But once we start locking rows like this, we hit an interesting potential problem. Let's have our two sessions each do a transfer of funds from one account to another, so that each must lock 2 rows for update. And just to make it interesting, session 1 will transfer from account 2 to 3, locking them in that order. And session 2 will transfer from account 3 to 2, locking them in the opposite order. So session 1 starts off beginning a transaction and locking row 2. And then session 2 jumps in and starts a transaction, locks row 3 and then row 2. And unsurprisingly, it blocks on the row 2 lock because session 1, of course, already has it locked. And then finally, session 1 does the second lock he wants on row 3. Now, before we even execute this final lock, think about what's about to happen. Neither session will be able to proceed. Why? The answer here is that both sessions will await a lock on a row that the other one already has locked, and neither can finish to completion and release their locks. So let's see what happens then. This catch-22 situation is called a deadlock, and it happens occasionally when 2 transactions work on the same data. MySQL detects deadlocks automatically, as you just saw here, and it solves them by picking one session to be rolled back while the other can roll back and that session's lock's released, and it leaves the other session to proceed. Session 1, after having been rolled back here, session 1 drew the short straw in that, can be restarted and will follow session 2, so the updates will happen sequentially and correctly. So we'll just commit the 2 transactions right now instead of following through with all that detail, but that's what would happen. And another question here. We had the sessions lock rows in opposite order, 2 then 3 versus 3 then 2. Would things have been any different if they had locked them in the same order, say both sessions locking row 2 and then row 3? And in fact, yeah, they would have been different. If, say, session 1 locked row 2 first, then session 2 would have been stopped at its request for locking row 2, leaving row 3 unlocked. Session 1 could proceed to lock row 3, finish its work, and then release its locks for session 2 to proceed. This points out a general way to avoid deadlocks. In SQL transactions, or any other context, deadlocking is a common issue in threading, operating system process control, and so forth. In any of those contexts, if 2 competing activities can be arranged so that they lock contested resources in the same order, then no deadlock will arise. So, the 2 practical takeaways from this discussion. Try to avoid deadlocks in transactions by locking rows in the same order in each transaction. And 2, it's not always possible to do this, and thus be prepared to restart a transaction if the DBMS forces it to roll back due to deadlock. Now, in the final segment, we'll look at the strictest level of isolation, serializable.